day, Doctor. I'm Shi Min. Today, I will with my teammates Kuan and Edmund to present our project. Our project is ARM-based implementation of speech control wheelchair. Next. And here is show our agenda. First of all, I will give a brief introduction to our project and also discuss about the problem statement and objective. After that, we will discuss about our workflow and coding, and we will show our demo video as well and summarize our project. Next. Before we go further, let me give a short introduction to our project. Our project is based on the keyword spotting. Keyword spotting is a task that detects keywords or phrases in utterances, and it enables hands-free speech recognition applications. And why we using ARM? Because ARM is low cost, low power, and flexible. Next, for our project problem statement is we found that the elderly and patient with impairment and cognitive disability is hard to use touchscreen-based or traditional wheelchair. So we set our objective to implement keyword spotting on wheelchair application by using ARM in order to ease the controllability of wheelchair for target customer and patients. Next, here's this diagram shows our flow chart for our system. First of all, we store the recognition words in the STM32. After that, when we receive the voice input, we'll go through the speech recognition or word spotting. And when the word is identified, we'll compare it with the store recognition words. And the corresponding subroutine or command will be executed and send it out to the output and in order to control movement of the servo motor. Next. And this slide shows the overview of keyword spotting on embedded system. Based on our reference GitHub link, the keyword spotting system we use are based on the DSCNN and also an FCC technology. Next. And now I'll pass the presentations to my teammate Kuan Yen.
So good day, Doctor. I'm Kuan Yen. So for the hardware side, we're using one nuclear board, 2 servo motor, 2 VL, 1 direction microphone, and 1 for the software wise, we're using one STM32 MSIDE for compiling and flashing code to the board for project implementation. Next. So this is the block diagram. So the combination microphone will receive the voice and then pass to the board, and the board will convert into command, pass to the 4-channel relay and the servo motor. Next. So this is a prototype, as you can see the hardware, and then we have the 2 wheel putting outside the container, and actually this container is our wheelchair. So each wheel will connect to 1 servo motor. Next. So here's the IOC pin out diagram. Next. So for the UART pin, we are using for PuTTY. PuTTY is the main purpose for display the command received from the microphone. So we are setting it to 115,200 peaks. For the word length, we are setting it to 8 peaks. Next. So for the I2S2, we are setting it to mode master receive, and the data and frame format we are setting to 32 bits. And the audio frequency we are setting to 8 kHz. Next. So for the timer, we are using 2 different timers but taking for the same clock source. So we are using timer 2 and timer 5. We are having one scenario is the go command. So the command case is for the moving forward, the wheel is needed to be rotated into 2. So for the timer 2, we are supporting the PWM to left wheel for rotating counterclockwise, while timer 5 is support PWM to right wheel for rotating clockwise. So for the frequency configuration, servo motor will support 50 Hz, while the API timer clock will supporting 45 MHz. First, we are taking the 45 MHz divided by the 50 Hz, and we got a 900K. So this 900K scale, we are using it we are implementing it by using the ARR and the pre-scala. So the pre-scala, we are setting it to 900, and the ARR setting it to 1000. So multiply it together back, you'll get 900K. The result of setting ARR to 1000 to represent as a 1000. The changing of the pulse width to other value can simply writing as percentage, as percent to CCR1 register. This will be cost easier to manipulate the real rotation. So this is the clock tree. So as you can see at the end of the clock tree, there is 545 MHz. Next. And the pre-scala we are setting to 900 and the AR will set to 1000 as I mentioned before. Yeah, that's I will pass to Edmund to continue the presentation.
Okay, hi doctor, I'm Edmund. So basically, I'll explain about this integrating KWS algorithm. So from the GitHub there, and from what based on Shi Min said about in the GitHub there, we have a ready-made data, and it already undergoes the MLCC and the DSCNN concept has been trained the data. And from here, we extract all the data in the form of source file and the header files, and we include them in the project directory. Okay, so right now, this is regarding the coding part. For the coding part, here we include the headers file, and here is the variable that we declared. And right now we reach until the subroutine parts. For the subroutine part, like what Kuan said just now, one we set clockwise and the one is set to anti-clockwise to in order to move in the same direction. And below here we set the LED according to the response that the mic detected. Okay, we have 4 motions: go, stop, left, right. Okay, and then in the while loop, the most important part for here is this one is the part that responsible for the mic to receive the data. And once it receives the data, it will receive in the form of two set of the audio buffer. First set, after it receive it, it will show it in the, it will send it to the putty there. So while the first set is sent to the putty there, the second set, it will receive the data simultaneously. Hence, these 2 sets of data. If it fails, it will show the error. And after that, this is the array which store the recognized word. So 12 word total. And after that, it receives the data, it will undergo the abstract features, classify, and for here, this is the part that responsible for the transmission of the data into the putty to check whether what is the command that it detected. And this is the one. And after that, we set the LED on the 4-channel relay, and this is the conditional part, which it indicates that which command it detected, and it proceeds to the related motion, left, right. So when it undergo left and right, it will stop right after the next command. And the go one. So basically, if the goal, it will continue to the wheel continue to move until it encounters the stop motion. Okay, so demonstration.
Go. Stop. Stop. Stop.
Okay.
Right. Left.
And as a conclusion, for this project, we successfully developed a ARM-based speech control wheelchair prototype. And the KWS, like I said just now, it built based on the MCC and DSCNN. And throughout this project, we encounter limitation challenges such as the sensitivity of the microphone is low due to the noise effect, and the accuracy of the word spotting is low. So sometimes low. So this is due to the this can be improved with the increased number of the train sample. So this is the reference that we got, and thanks a lot, Doctor.